All right, at the end of part 4, we talked a little bit about the classical ideas of galaxy evolution and how spirals probably formed first when they were sort of spherical in shape, forming some stars and globular clusters, and then because they had a lot of rotation, you ended up with a rotating disk of leftover material, and then that leftover disk had intense star formation to become the spiral arms. We now think that ellipticals, instead of forming this way, at least large ellipticals, are mostly, we think, formed by collisions and what some people call galactic cannibalism, galaxies swallowing each other and colliding. Galaxies often collide. In fact, in several billion years, it's thought that perhaps our Milky Way will actually collide with the Andromeda Galaxy, and we will end up as an elliptical galaxy. But these things take billions of years, and so when we look into the universe, we're really only seeing galaxies in a snapshot in time. Even colliding galaxies won't change from year to year. We'll only see them in the process of colliding. But what we do see is that there are these galaxies called starburst galaxies, which are formed when galaxies collide, and because of the collision, even though it's very, very rare and almost impossible for two stars within these galaxies to actually collide, the dust clouds do. The clouds of gas and dust interact, and the increase in density that's caused by this collision will make a burst of very violent and rapid star formation and pretty much use up all the excess gases that were in the disk of these spiral galaxies as they collide. And so what you end up with is a galaxy devoid of gas and dust, where the stars will exist and then eventually die out, and you end up with a galaxy that's elliptical in shape. Okay. Again, these theories are really in their very early stages, and who knows, 10, 20 years from now we might have a different story. Okay, so let's go on then to finding the mass of galaxies. One thing you notice if you ever see a galaxy through a telescope is that they don't look very interesting. They certainly don't look like these pictures of the long winding spiral arms. It's very difficult or almost impossible to see spiral arms in a telescope unless you have a really, really huge one like an observatory class telescope. They are incredibly faint, and most of the light from the galaxy comes from this fuzzy middle part. So when you see a galaxy through a telescope, they generally look like fuzzy blobs, and they're not all that impressive looking to your unaided eye. Well, even your aided eye. They certainly don't look as spectacular as they do in these long exposure images that you get with these highly sophisticated cameras and telescopes. What we have here is a galaxy that has a very noticeable bright core and then fairly wispy arms. You would imagine then that most of the stars are at the center because that's where most of the light is coming from. And if that were true, the rotation of this galaxy would be fairly predictable. Okay, let's think about this. The galaxy at the center, when the sun, for example, which would be somewhere out here if the sun were in this galaxy, the sun would go round and round, and its velocity would be determined by two things. It would be determined by the distance from the center to the sun's orbit. So let's say the sun's orbit is right at the edge of this spiral arm here. It would be determined by the distance from the center. Okay, and the farther the distance, the slower it would go. But it would also be determined by the amount of stuff inside its orbit. And the more stuff inside its orbit, the faster it would go. And so to find the mass of a galaxy, it's useful to make something we call a rotation curve. A rotation curve plots the velocity of bits of a galaxy versus the distance from the center. And that's fairly easy to do with a spiral galaxy, although you wouldn't pick a spiral galaxy that's face-on like this. You would do one that's edge-on, because then the material in the outer arms would be coming toward you or going away from you. You could get the velocity from the Doppler shift. So rotation curve is where the orbital velocity of objects from a galaxy's disk, it depends on the force of gravity from material inside the orbital radius of the object. Okay, so what we're going to try to do here is say, okay, what's the velocity? We're going to make a graph of velocity increasing upward versus radius from the center increasing to the right. Okay. So a rotation curve is obtained by finding the velocities of gas clouds in the spiral arms, or stars for that matter. We do gas clouds in our own galaxy because we can't use visible light from the stars because those are blocked. So we would use 21 centimeter radiation from the neutral hydrogen clouds for our particular galaxy. But for other galaxies, we can actually use spectral lines from stars. Okay. The orbital velocity, the square of the orbital velocity is proportional to the mass inside over the radius, the radial distance. Now, near the center, the density seems to be so high. So near the center, the density seems to be so high that as you move outward from the center, you would expect to go faster and faster and faster in your orbit. Because even though you're getting farther away from the center, you are increasing the amount of stuff inside your orbit more than the velocity is decreased by increasing the distance. Okay? So these two factors are interacting here. The mass inside is increasing and the distance from the center is decreasing, but the mass inside is winning because that's increasing at a greater rate than the radial distance is increasing. So what you would expect to happen if you were to draw this graph is you would expect that the velocity would go up very, very steeply from the center as you increase. Okay. But then when you get to this point out here, it looks as though the stars thin out. And so you would expect the velocities to drop because the radial distance is getting greater, and therefore there's not enough material to compensate for that greater distance. So out here, it's more like the orbits of the planets in our solar system, where the farther you go from the sun, the slower the planets go. Okay, Mars goes around the sun more slowly than we do. Jupiter goes even slower, Saturn even slower, Uranus and Neptune slowest. Okay. So we would expect it to be kind of like this. We would expect a decline, which is something your book calls a Keplerian velocity, because it's what we would expect from Kepler's third law. However, that's not what happens. Okay. So near the center, the density is high. The mass inside the orbit gets a lot bigger as you move away from the center. The visible material in the galaxy then thins out, so the distance dependence should dominate. So that's where we should get something like this decline. Okay. However, that's not what happens. Okay, that is not what happens. What actually happens, let me change the color of my pen here. What actually happens is our galaxy rotation curve does rise, but then it reaches a plateau and remains fairly flat as far out as we can observe. Like that. So what really happens is these velocities stay the same. And there's no way we can account for this by the gravity of just the light-bearing stars inside the orbits of these objects here. So for example, if we calculate the velocity of a star way, way out here in the galaxy, it's going way too fast for the gravity of the things that give off light, the stars, but also the H2 regions and the gas and dust that we can see with other wavelengths of light. It's going way too fast to be held into the galaxy, and yet the galaxy survives. The galaxy does hold together. And it's not like we just need a little extra mass to hold these outer stars in. We need a lot more mass. So it turns out to have a flat rotation curve like this, you need about 10 times more mass than the estimated mass of all the stars in this galaxy. So a galaxy like this might have 200 billion stars. It might be somewhere like 100 billion times the mass of the sun. But it needs something like 10 trillion times the mass of the sun. It needs it needs something like 1 trillion times the mass of the sun, or 1 trillion times the mass of the sun, about 10 times more. It needs about 10 times more mass than we see. And that is a very, very important problem, sometimes called the missing mass problem, but what we now call the dark matter problem. The outermost stars of the Milky Way and other spiral galaxies are orbiting much faster than we'd expect from the matter that we can detect inside the galaxy. Now, by detect, what I mean is we're not just talking about matter that we can see with visible light. We are talking about matter that we can detect with any means, by radio telescopes, infrared telescopes, you name it. Okay, so again, here's a spiral galaxy with a very bright core. We'd expect the velocities to be increasing here and then fade off as the light fades off. But no, that's not what happens. From other galaxies, we see the same rise and flattening. Rise, plateau. Rise, slightly decreasing, but hardly at all. This suggests that galaxies have much more mass than we can see. And again, see is in quotation, because I mean see by any means, not just our eyes. Okay. So we think that massive, dark, extended halos are needed to account for the extra gravity. And again, we don't mean just a little bit of extra gravity. We mean a lot of extra gravity. And there's more evidence for this. This was first discovered in the 1970s by a woman named Vera Rubin. A similar effect was actually discovered in the 1930s by an astronomer by the name of Fritz Zwicky. When you look at galaxies in a cluster, they're moving around. We can figure out their typical velocities from their Doppler shifts of their spectra. And what we find is they're moving around too fast for the cluster to hold together due to its gravity. And yet the cluster does hold together. So how much gravity do we need to hold the cluster together? About 10 times more than is accounted for by the visible or detectable light. Okay. So galaxies and clusters are also moving around too fast to be kept in the cluster by the gravity of luminous matter. So here we're not talking about the rotation of an individual galaxy like this one here. What we're talking about is the motion of these galaxies within the cluster, the sort of random motions of the galaxies within the cluster. Gravitational mass must be 10 times greater than the detectable mass for the clusters to be gravitationally bound. So, that's a lot. That means that 90% of the universe is stuff we can't see. Luckily, there is a way to detect some of this matter. We do this by using a little help from Albert Einstein. It turns out that general relativity, the theory of general relativity, says that matter can bend light. So if you have an invisible object, say like a black hole or some other object that's too dim to see, and it's in front of a distant source, the light will bend in such a way to make kind of a ring around that invisible source. And we can use that to detect dark matter as well. Okay. For example, galaxies can distort the image of more distant galaxies and make these sort of blue rings or blue arcs. That is the same effect as we see here. Right? Well, we'll have to continue this in our next installment.